Convolution. Convolution. What is convolution? So convolutions is a, in a way, sorry. So in a way, it's a operation, so just like Laplace transform, right? But Laplace transform going to apply on this particular operation. So convolution is a mathematical operations that combines two functions to produce a third functions, right? Which expresses how the shape of one is modified by the other. So let's think about this. When you play an instrument, right? An instrument, when you play a song, the song just not have one note, it have multiple notes, and it goes one after the other. Right? So I don't know how you, if you play any instrument at all, but let's say you play a piano. Sometimes you don't hit the pedal. When you hit the pedal underneath, when you use your leg to hit the pedal, is kind of keep the sound going a little bit further, right? Before you end that note, you hit another note, right? So you have that combinations of multiple notes, and also by hitting the pedals, you have a something called the you have an input and you have a response system, right? So the response system give you different type of tune, different type of amplifications, things like that. You can sit in a room, right, and you sing into a microphone, right? You have a certain sound, you have a certain level of noises. But if you don't place the amplifier in the correct positions, the sound that you create will go into the amplifier, and it kept increasing the noise. And sometimes you in the room, you in a concert, you in a hall or something like that, and the noise just keep increasing until it hits a very high pitch noise, right? Something like that. So the force or the input that you give in, right, which is your voice, will depend on the environment or the system that you're working with. Therefore, you will have a different response, right? Sometimes you're in a very quiet room and is have a lot of stuff around you. Then when you make a noise, the voice or the noise cannot go far, right? The response, there's no echo at all, something like that. But if you're in the room, very empty room, you don't have any stuff in the room at all except just the microphone. When you create a sound, the sound will, that's the force, that's the input that you put in. Now the response can be that you have an echo back into your ear. Okay. So that is the idea of convolutions, right? So you have two functions using the convolutions. You will create a third function, and the third function depends on these first two functions, right? One function can be an input, and the other can be a response to that input. All right. And so the idea of this lecture is to understand the idea of convolution as the process of combining two functions to produce a third function. And I'm going to integrate the convolutions graphically, where it's coming from. Okay. And I hope you're familiar with some of the properties of convolutions and compute convolutions integrals. So convolutions has many properties that are similar to the regular multiplications. Right? You can have a commutative property. So you have two functions f and g. If you have f convolute with g, it's going to be the same with doing g convolute with f. You have distributions property, you have association property, you have a convolutions of a function with zero. Right? Things like that, that is very similar to the regular multiplications that you have done in grade school. And at the end, I'm going to ask you to do some evaluations on Laplace transform and the inverse Laplace transform of convolutions integrals. Okay. And convolutions occur in many areas in engineering, and when you work with engineering materials, you have to work with a system, or it usually depends on the system, that is called the linear time invariant system. So what is linear time invariant system? So first you break it down into two different terms. Right? The first one is the linear system, and the second term is the time invariant system. So the linear system, so given a system, if its input is scaled by a certain factor, its output is scaled by the same factor. Right? Then that system is called a linear system. Let's say you have an input, which is x in this case, and the linear system that you have, right? The output is y. Now, if you scale the input, right, by a factor alpha, the output is going to scale by the same factor alpha. Okay. Now, what is the time invariant system? So a time invariant system is one in which a given input always produces the same output apart from the shift in time, regardless of when the input is applied. You can think of this particular system, the time invariant system, as the headphone cancellations, noise cancellation headphone. Is that the thing? Any of you have that? Right, Esther, you have that. So when you hit when you put on your headphone, noise cancellation headphones, right, it's cancel all the noise in surrounding area. Right? When you put that on right now, you can only hear my voice, right, and hopefully no other noises from the outside. Now, when you do that, and then let's say tomorrow when you do the test, you put on the headphone, it's going to produce the same output. That is, you only hear, let's say, my voice or the voice that whatever who is speaking, right? And no other noises around in the surrounding area, right? So the input is just the music that you hear and no other noises from the outside. You do this now, or you do it tomorrow, or you do it next week, it's going to be the same thing, right? So that is the time invariant system. The given input always produce the same output, right? The difference is that you put on the headphone right now or you put the headphone tomorrow, right? This it's going to experience the same thing, right? And hopefully the headphone can be kept for a long time. Let's say 10 years from now, it's going to produce the same output. That is just the music, no other noises around, right? So that is the time invariant systems. All right, so let me annotate a little bit of information here. And so for the linear system, obeys the superposition principle. All right, so the superposition principle you have seen before. For instance, you have Laplace transform is a linear operator. So linear Laplace transform of the linear combination is the linear combinations of Laplace transforms. You can do that, of course, because a Laplace transform is the linear operator, and because of that, it obeys the superposition principle. So for instance, you have linear combinations of alpha times x1 plus beta times x2. The output's going to be alpha times y1 plus beta times y2. Right, so that is the linear system, that to give you the idea that it's obeys the superposition principle. So here, this is the superpositions principle with linear scaling factor. And for the time invariant system, so you have two scenarios here. The first scenario is that you have a time invariant system occur at time t, and another linear system, another time invariant system occur at t minus t0 time. And so the output y of t and y of t minus t0 are identical. So the only if difference is that the output due to the input x of t minus t0 is shifted by a time t0. So the two outputs should be identical. So that's what you need to see in most of the system that you're working with. For another example is that you turn on the computer, right? It should turn on. It should give you the home screen. Right? You see it now. You should see it. The same thing tomorrow, so on and so forth. That's exactly what you want to happen in your computer, right? You don't want your computer to get turned on now, and then could not turn on tomorrow, something like that. And one note here, we work with the time invariant system because time invariant system are modeled with constant coefficients. Coefficient equations. So and that's why most of the equations that you have is, let's say, the second order differential equations, right? But is a linear second order differential equation with constant coefficients. Okay, and of course depends on the forcing term. You may have homogeneous equations or no homogeneous equations. But because of time invariant system that we want to work with, most of the differential, all of the differential equations that we have so far, or most of the differential equations that we have so far is with constant coefficients. So a constant coefficients differential equations means that the parameter of the system are constant. Okay, or not changing over time. Okay, so that's the linear time invariant system, right? And let's move on to convolutions, right? So the definition, I give you the definitions earlier. That's a convolution is a mathematical operations that combines two functions to produce a third function, right, which expresses how the shape of one is modified by the other. That's the process of convolutions. Now, the motivations for this convolution is that in a linear time invariant system, any complicated output can be thought as the sum or integral of shifted scaled impulses. Okay, so the linear system is here in the concept because you want to sum up all the informations, and the time invariant system because you want to sum up the informations not only now but also a little bit in the future. And it can be represented here in this graph, right? So you have this type of information. This information is a continuous curve, right? But sometimes you don't have continuous curve. You have a discrete information. That is, let's say you want to measure the weather, right? So and the weather it can go up and down, right? So this is the information about the weather in this time of the year. This time of the year is go up, it come down a little bit, something like this. And all the information you collect and you can put it in here in the graph, and kind of join the continuous curve to make the predictions, something like that. So the input f of t can be built from infinitely many infinitesimal impulses. Okay, so you can make it into smaller and smaller impulse to get the information of the continuous curve f of t. Okay. If the system responds, so this is for the input. Right? If the system responds to delta t, which is the impulse functions, and the response is going to be h of t. Right? So let's say you have a you watch a baseball game and you hear the bat connected with the baseball, and you hear a very loud noise to go up like this instantaneously, and then of course it's going to come down and eventually going to go to 0. And now later another heater come to bat, and you see like kind of a similar noise, a very high-pitched noise going up all of a sudden, and then it eventually going to come down. Okay, so the response, as you can see, is very similar to what you see in the response of h of t, even though it gets shifted later to another place. Now, by adding all the scale shifted impulse responses together leads you to a convolution integral. And the convolution integral is given as, right, so f, this is the notations for the convolutions. Right, so this start right here. So f convolute with g of t is equal to the definite integral from 0 to t, right, of f of tau g of t minus tau d tau. Right, so this notation is called tau. It's a Greek letter. Okay. Right, so f of t is the function. Now you have f of t and g of t, right? So f of t is how a force input changes over time, right? So how the force input changes over time. Okay. So that's the input force. Now g of t has gonna give you the information that how the system responds to a single impulse of force. Okay. And the convolutions here of convolute with g of t is the total displacement at time t. Okay, so this displacement, total displacement caused by all the impulses from 0 to t. It can go up, it can go down, but the combinations of all of this can be calculated and give you the convolutions of two functions. Right, so mathematically, the definitions of convolutions, right, convolution of piecewise continuous functions is the functions f convolute with g I have a new pencil and it just doesn't work the way I wanted. Sorry about that. So this one is a convolution function. Okay. So given by this formula, so f convolute with g of t equal to the integral from 0 to t of f of tau times g of t minus tau d tau. Okay. And as you can see, it's a very straightforward calculation. It's a definite integral, nothing crazy there. So here, find convolutions of functions. You have two functions, f of t, which is e to the 3t, and g of t equal to e to the 5t. You can think of this as f of t as an input and g of t as an output. So f of t is equal to e to the 3t. So for instance, you in a room, right? Very empty room, and you place a amplifier at the locations at which, when you, let's say, voice it into the microphone, you have a noise, and that noise going to go through the amplifier, and amplifier placed at the locations, it's going to fit back into the microphone, and it create a higher pitch sound, and it's going to keep going like this as a loop. Right. So this is going to be a loop of positive feedback, and that's why you have an input as e to the 3t, and then the output e to the 5t, which is increasing the amplifier information. Okay, so that's a scenario that we can think about. Right? So how would you find the convolutions of these two functions? So the convolutions of these two functions using the definitions of convolutions is definite integral from 0 to t of f of tau times g of t minus tau. So f of t is f of tau is e to the 3 tau, and g of t minus tau is e to the 5 times t minus tau d tau. Okay, so you use regular definite integral to calculate this integral. Right? So first I'm going to distribute 5 into the parenthesis on the exponent here, and I get the definite integral from 0 to t of e to the 3 tau times e to the 5t minus 5 tau d tau. And because the integral is with respect to tau, e to the 5t becomes a constant in this context. So you can pull e to the 5t out of the integral operations. And you get just e to the 5t times the integral from 0 to t of e to the 3 tau times e to the negative 5 tau d tau. Of course, you combine these two exponential functions together, you get e to the 5t times the integral from 0 to t of e to the negative 2 tau d tau. Evaluate this integral. If you know the formula, you can just give the answer. If you don't know, you can use integration by substitutions to evaluate the integral. But this one could give you e to the 5t times negative 1/2 times e to the negative 2 tau, evaluate at 0 and t. And you have negative 1/2 times e to the 5t times e to the negative 2t minus 1, because e to the 0 is equal to 1. And then you distribute e to the 5t into the parentheses, you have negative 1/2 times e to the 3t plus 1/2 times e to the 5t. Okay, so that's the results. and this result is going to be, is a result, right? But it's going to be useful when you incorporate that into a system of initial value problem, right? That is, you include the differential equations, the non-homogeneous differential equation, and also the initial conditions. Right, some of the properties of convolutions, so as I mentioned, they have some of the very similar properties to the regular multiplications. You have commutative law, you have distributive law, you have associative law, and you have a zero property. Right, so commutative law, that is f convoluted with g is equal to g convoluted with f. That means no matter what the order you do the convolutions, you should see the same information, so you should see the same results. Distributive property, if you have f distributed with g plus h, that is going to be f convoluted with g plus f convoluted with h. Now for associative law, you have f convoluted with g first, and then whatever result you got, you do the convolution with h. Or you perform the convolution between g and h first, and then apply the convolutions with f later. You should see the same results. Okay. For the zero property, you have function f convoluted with zero functions, or zero convoluted with f, the result is zero, right? So very similar to the regular multiplications or the ordinary multiplications. Alright, so I want to give you another example here in terms of finding the convolutions of two functions. Again, very similar to what you see in the first example. You just use the definitions of convolutions to do these calculations. So you can choose f to be e to the negative t and g to be psi of t. Right, so f convoluted with g of t give you the definite integral from 0 to t of f of tau d tau. For f of tau is e to the negative tau. And d tau is, f of tau times g of t minus tau d tau. So g of t minus tau is going to be psi of t minus tau d tau. Now, so when you encounter this type of problem, you can see that you can do e to negative tau times psi of t minus tau. But remember, convolutions is commutative, or you can rewrite this as the definite integral from 0 to t, and you choose f of tau as psi tau, and g of t minus tau can be e to the negative t minus tau. So you can switch these two functions together because of the properties of the commutative. Right? So f convoluted with g is the same with g convoluted with f. You can do psi of tau times e to the negative t minus tau. So either one should work for you in terms of the results. Okay. So let's see that you, let me do this integral. So let me start with this integral first. So instead of, so I'm going to let u equal to exponential functions. And for the exponential function, I'm not going to break it down into e to the negative t plus tau. I'm going to keep the exponent as that as it is. So you let u equal to e to the negative t minus tau. You take the derivative of this. You have du equal to negative e to the negative t minus tau. Okay, dt. Sorry, d tau. Let me be careful here with respect to tau. So sorry. So just e to the negative t minus tau, okay, d tau, because negative distribute into the parenthesis, negative with negative become positive. So, and you take the derivative with respect to tau, therefore there's no negative in front of the exponential function. Now you get dv times psi of tau d tau, and therefore v is equal to negative cosine of tau d tau, and the convolutions becomes f convoluted with g of t is equal to u times v, negative of e to the negative t minus tau, times cosine of tau to evaluate at 0 and t, plus the integral from 0 to t. Usually it's minus v du, but negative with negative become positive, so that's why you have positive here. So plus the integral from 0 to t of cosine of tau times e to the negative t minus tau d tau. Alright, so now you run into the same problem here, that is you need to evaluate this integral using integration by parts. So this is the second time you do it. And remember, when you do the integration by part twice, the second time you should follow the same structure as the first time. That is, you let u equal to the exponential functions, and dv is equal to the trigonometric functions. So you let u equal to e to the negative t minus tau, and du is equal to e to the negative t minus tau d tau, and dv is equal to cosine of tau d tau, or v is equal to psi of tau. Okay, so the convolutions again becomes negative e to the negative t minus tau times cosine of tau, evaluate at 0 and t, plus u times v, which is e to the negative t minus tau times psi of tau, evaluate at 0 and t, minus the integral from 0 to t of, so this one is t, psi of tau times e to the negative t minus tau d tau. Okay. And again, you run into this problem, you have an integral of psi of tau times e to the negative t minus tau. This one's precisely the convolutions that we're looking for. So you substitute this instead of the convolution integral, you just write the convolution between two functions. And then later you're going to combine these terms and these terms together. Okay, so I'm going to move this to the left hand side to get 2 times f convolute with g of t equal to negative e to the negative t minus tau times cosine of tau plus e to the negative t minus tau times psi of tau, evaluate at 0 and t. Okay, so now it's just the evaluations. You get 2 times f convolute with g of t. Evaluate this two function at 0 and t. You have negative e to the negative t minus t times cosine of little t plus e to the negative t, because tau is equal to 0, times cosine of 0 plus e to the negative t minus t times psi of little t plus, minus e to the negative t minus 0 times psi of 0. So psi of 0 is equal to 0, so this term is going away. Cosine of 0 is equal to 1. Therefore, you get this one to be negative e to the 0, which is 1. So the first term gives you negative cosine of t. The second term is plus e to the negative t. The third term gives you plus psi of little t, and that's it, right? And to get the value of the convolutions, you divided both sides for 2. Alright. Any questions on this calculations? Let's take a little bit of time and work to do so. Okay.
Since once we get to these cyclic integrals, after the second time, if we start with the same function, we can then just simplify.
Yes, you can't just combine like terms. And it's not only for the convolutions, but in general, if you have this, exponential functions and sine with sine in or cosine functions, then you will see the cyclic or integral as a loop, right? You go back and forth between sine times exponential function and cosine times exponential functions, and you should be able to combine them like this, right? That means you move these informations to the left hand side. And if for some reason you see these two terms kind of cancel out altogether, that means you're doing something wrong, and you have something wrong in your calculation. So be careful with that. So it's a good way to check if the calculation is correct or not. Okay.
Gotcha.
Now for Laplace transform. So if you have capital F of s, which is Laplace transform of a function little f of t, and g of s is the Laplace transform of little g of t, You have that information on Laplace transform. Then h of t is equal to f of t convolute with g of t, and the Laplace transform h of s is the Laplace transform of h of t, or the Laplace transform of f convolute with g. Alright, so this is a fun thing about convolutions. The Laplace transform of a convolution is going to be the Laplace transform of f of t times Laplace transform of g of t. How convenient is that? And therefore, this is going to be equal to f of s times g of s, and this times just the regular multiplications. And now if you have a product of two functions here, f of s and g of s, and capital F of s is the Laplace transform and g of s is the Laplace transform, then when you take the inverse Laplace transform to get little h of t, or the inverse Laplace transform of f of s times g of s, is going to give you the convolutions of two functions. So it's very straightforward. And you get the convolutions, and then you evaluate the convolution using the definitions of the convolution. Okay. Now let's apply that to this particular function right here. So the function you have is capital H of s equal to a over s squared times s squared plus a squared. So you find the inverse Laplace transform, that is, you want to find h of t equal to the inverse Laplace transform of a over s squared times s squared plus a squared. Now you can separate this into two fractions multiplied together. So that is the inverse Laplace transform of 1 over s squared times a over s squared plus a squared. Okay. And when you look at this, when you go back to the Laplace transform table, you look for 1 over s squared to see if there is any Laplace transform related to 1 over s squared, and you find if there is anything related to a over s squared plus a squared. So let me go to Laplace transform table. So for 1 over s squared, you have this particular formula, which is number 16, right? So 1 over s squared indicate that n is equal to 1. So 1 over s squared, which is the Laplace transform of the function t. Okay, and for a over s squared plus a squared, you have formula 24. In this case, b. But this is the Laplace transform of psi of at. Right? So a over s squared plus a squared is the Laplace transform of psi of at. So you go to here, and you get the inverse Laplace transform of t times Laplace transform of psi of at. And this give you t convolute with psi of at. Right. Very simple, right? Or it can be written as psi of at convolute with t. So it doesn't matter which one because convolution is commutative, right? And then you can apply this you can use definitions of convolutions to evaluate the convolutions, right? So that is, so h of t is equal to the definite integral from 0 to t of t minus tau times tau times psi of a times t minus tau d tau. Or you can write this as 0 to t of psi of a tau times t minus tau d tau. Okay. And then you can evaluate this integral. Okay. Any questions on this?
No. For the final exam, will we be able to use Laplace transform tables?
Yes, I will give you Laplace transform table I will. So what I'm going to do is I'm going to use prepare the test. Of course, today I'm going to prepare the test, and depends on whatever questions we have. I will include some of the Laplace transform table, not the entire table. It's too much information there. Too many unnecessary informations that you don't need at all. So I will include some of the very specific formula so that you can look at those formula for the Laplace transform. Okay.
Okay, thank you.
And then, I mean, since convolutions came after Laplace transform, so does that mean every Laplace transform we've done is a convolution waiting to happen?
Yes, yes, because where is this? So for the definitions here, right? When you look at this, right? So it's just a formula. We didn't have time to go into too much information about what's going on with this particular formula. I'm gonna change the pen to another pen. Anyway, sorry. So when you look at this formula, right, you go back to the notes, particularly the impulse function note.
Yeah.
Okay, good. So this is lecture 17, impulse function. So this is the solutions that we got, right? Here, the shifting properties. So the shifting properties is here, right? So you have the improper integral from negative infinity to positive infinity, and you have f of t times delta of t minus t0. So delta t, so direct delta function, is in a way a very special case for the unit impulse functions. Okay. Now the unit impulse function is that it's just one function occur at a very specific time, in this case t0. Okay. Now what's going to happen is that I mentioned at the beginning of the class is that you don't have just one impulse, you don't have one signal, you have a multiple signal, you have a continuous signal, right? And you have this type of signal. Let me go back to convolutions here. Okay, so you have this many signals, right? So the red one combined together. So the informations on the formula related to the convolutions here is eerily very similar to the distributions that you see earlier from negative infinity to positive infinity of f of t times the delta functions, right? Now that calculation is only for one signal, right? And g, the calculation here for convolution is f of tau times g of t minus tau for so for the integral from 0 to t. So you are right about that, Tarun. So all of the calculations that you see earlier, like in for Laplace transform, is in a way can be done using just convolutions, because the signal that you have is just not one signal but multiple signals, and sometimes you have continuous signal, right? So that's why Laplace transform in here is convolution is very important. So let's say you in the hospital and you work in the hospital and you want to check the heart rate of someone, and the heart rate is not just one heart rate, it's just one, it's not one strike, right? Is a information of how the heart is beating, right? It's just continuously beating, right? You don't want it to stop at any moment. And so, but if you know how to do the calculations for one bit of heart rate, then it's okay for you to apply convolutions for the continuous pattern of that heart rates, right? And therefore convolutions informations. And that's why the motivation here is that the input can be built from infinitely many infinitesimal impulses. You get the idea? Okay, so you have this one, you have this step, you can evaluate this using the just the regular definite integral, right? So here you can do integration by parts again. You have u equal to t minus tau, and then du equal to negative d tau. So remember, this is with respect to tau. And dv is equals to psi of a tau d tau, or v is equal to negative 1 over a times cosine of a tau. And therefore, h of t is equal to negative 1 over a times tau times cosine of a tau, evaluate at 0 and tau t, minus v du. So minus is plus, when not minus is minus 1 over a times the integral from 0 to t of cosine of a tau d tau. Okay, and then you evaluate this function at t and 0. So when you let tau equal to t, these terms will go away, and you just evaluate at 0. So let me add another page here. So h of t equal to negative 1 over a times t minus t times cosine of at plus 1 over a times t minus 0 times cosine of 0 minus 1 over a times another 1 over a because you take antiderivative of cosine of a tau. This gives you sine of a tau, evaluate at 0 and t. So this term is 0. So you have 1 over a times t, cosine of 0 is 1, minus 1 over a squared times sine of at. Okay, because sine of 0 is equal to 0. So that's the convolutions that you get, or the Laplace transform of convolution. Okay. Now we're going to move on to the last example, that is find the inverse Laplace transform of this function 1 over s squared minus 10s plus 16. You will see how this is very convenient for us in terms of doing the calculations. So the inverse Laplace transform of this gives you h of t. So inverse Laplace transform of 1 over s squared minus 10s plus 16. And in the denominator, you can actually factor it into s plus 8, sorry, s minus a times s minus 2. Okay. So before this lecture, what you should do is that you separate this fraction into two different fractions using partial fraction decompositions, right? And take a little bit of steps to do, a little bit of time to do that, a few more steps to get to the answer. But here, you don't have to do the partial fraction decomposition whatsoever. What you do is that you just need to rewrite this as 1 over s minus 8 times 1 over s minus 2. And then you look for the informations related to 1 over s minus a and 1 over s minus 2 in the Laplace transform table. So that is, go to the Laplace transform table, and you have this formula. So that is e to the at, Laplace transform of e to the at equal to 1 over s minus a. So 1 over s minus 8, the Laplace transform of that is e to the at, and 1 over s minus 2, the Laplace transform of that is e to the 2t. So here you have the Laplace transform of e to the at times just the regular multiplications of Laplace transform of e to the 2t. And therefore, the result e to the at convolute with e to the 2t. So that's the result, right? So you avoid the integration, partial fractions decompositions altogether, and just focus on. So sorry, let me charge my computer. Just focus on calculating the definite integral. So from here, you have the definite integral from 0 to t of e to the a tau times e to the 2 times t minus tau d tau, or you can do the integral from 0 to t of e to the 2 tau times e to the a times t minus tau. It doesn't matter which one you go with, you should see the same results. Okay, so let me do the first one. Let's change the color here just to avoid confusions. So e to the a tau times e to the t times e to the negative 2 tau d tau. So e to the 2t in this context is a constant, so you can pull that out of the integral operations. So e to the 2t times the definite integral from 0 to t of e to the a tau times e to the negative 2 tau. You combine them together, you get e to the 6 tau d tau equal to e to the 2t times 1 over 6 times e to the 6 tau, evaluate at 0 and t. So you have 1 over 6 times e to the 2t times e to the 6t minus 1. Or you have 1 over 6 times e to the 8t minus 1 over 6 e to the 2t. So that's the result that you're looking for. Alright. So that's it for me. I didn't want to place this in to include a definite I don't want to include an initial value problem. It's take a little bit of time to go over everything. So the most I'm going to ask you is probably one question related to the concept of convolutions, and then ask you to find the inverse Laplace transform of this type of functions where you can apply the convolutions integral. You okay with that? All right. So even though I didn't include the initial value problem, but when you do the calculations, right, you know how to tackle the initial value problem, take the Laplace transform on both sides of the equations. When you arrive at this type of problem right here, where you need to apply the inverse Laplace transform, okay, you can either, now you know two techniques to tackle this particular inverse Laplace transform. Either you can use the partial fraction decomposition, or you can use convolutions. Either one should give you the same answer. You got it? Okay. Now again, for the convolutions, right, you get to the convolutions, you have to keep going and evaluate this convolution using convolutions integral to get the final results. Okay. You cannot just leave the result at this. You okay with that? All right. So that's it for me today. We're going to have the test tomorrow at 8 o'clock. And I have all the requirement in the announcement already. So let me know if you have any questions on that. And the topics that I'm going to cover again is from the beginning of the semester up to this point. But the focus, most of the questions you see in the test will be on the second half of the course, even though there's just a few questions related to the first half of the course.